Hello again. This is Math 2134 coming to you from the College page, and the title of this lecture is Partial Derivatives and Such. And as always, I encourage you to be an active learner as you watch this video. In this video, we'll talk about what is the partial derivative of a function and how do you find it. We will evaluate these partial derivatives. That means plugging in numbers and getting numerical values. We'll use differentials of a multivariate function to estimate the change in the function. And we'll also find the 4 second-order partial derivatives of a function in 2 variables. By way of introduction, consider the function f given by z equals f of x, y equals this expression, and you see there are x's and y's all over. But suppose we fix y to be 3. Then every place there is a y, we can put 3. So we'll have f of x comma 3 is equal to, we do all of those substitutions and finish the calculation, and we end up with 27x squared plus 3x plus 36. Note that we now have a function of only one variable, the x. So taking the first derivative with respect to x of this function, we get 54x plus 3. Make sure you follow these calculations. It's good review for the final exam. In general, without replacing y with a specific number, let's regard y as being a fixed value, whatever it is. Then f becomes a function of x alone, and we can calculate its derivative with respect to x. This is called the partial derivative of f with respect to x, and is denoted by, and this is a different symbol. It is a script d over a script d. So it's partial of f with respect to x, or we could say it's the partial of z with respect to x. Now let's consider this function then, which is the same, but again we're saying y is a constant. So everywhere there's a y, we treat it as a constant. So again, we're going to take the derivative of this with respect to x. And so when we do that, we're treating these as constants. So the y cubed just sits there, the y just sits there, and the y squared is just a constant. So 4y squared is also a constant. So when I take the derivative here, I get 2x y cubed plus y. Now, similarly, we could find the partial of f with respect to y, or the partial of z with respect to y by fixing x, treating it as a constant and calculating the derivative only with respect to y. So here is z, and we're going to say that x is fixed. So x squared is a constant, x is a constant, and 4 is certainly a constant. And so when we take the derivative, it's the partial with respect to y. And so what's going to happen is the constants just sit there, but I take the derivative with respect to the we're taking the derivative, the x's just sit there, and we're taking the derivatives with respect to y. So we get x squared times 3y squared plus x times 1 plus, and then this, I'm taking the derivative with respect to y again, so that's going to be 8y. And when we simplify, we get this. Here's the definition of partial derivatives then. And since calculus is the study of limits, you're not going to be surprised that this is a limit. So suppose we have z equals f of xy. The partial derivatives, there are more than one with respect to x, and then with respect to y are the partial of z with respect to x is the limit as h goes to 0, and this is f of x plus h comma y minus f of x comma y over h. You see only the x varies. Similarly, the partial of z with respect to y is the limit as h goes to 0 of f of x y plus h minus f of x comma y over h. You see the only thing that changes is the y. Now we can find partial derivatives of functions of any number of variables. And since earlier theorems for finding derivatives apply, we rarely need to use this definition, but that is the definition, and calculus remains the study of limits. Examples are always worth 1,000 words, so let's look at an example. Suppose w is equal to x squared minus xy plus y squared plus 2yz plus 2z squared plus z. Now you see w is a function of 3 variables, x, y, and z now. We want to find the partial of w with respect to x, then the partial of w with respect to y, and the partial of w with respect to z. Okay, when we're finding the partial of w with respect to x, we treat x as a variable and y and z are constants. And so the only variable is x that we're talking about. And so when we take the derivative, this is going to be 2x, and this is going to be minus y, and the rest of these are just constants. And so that is the partial of w with respect to x. To find the partial of w with respect to y, we regard y as the variable and treat x and z as constants. Okay, so that means y is the variable. So we're going up and we're looking at this expression again. And so what's going to happen then when we take the derivative with respect to y? We're going to get 0 from this term. We're going to get minus x from this term. We're going to get 2y from this term. We'll get 2z from this term. And the rest of these are constants, so this is what we get. To find the partial of w with respect to z, we regard z as the variable and treat x and y as constants. Okay, so x and y are constants, so this is a constant, this is a constant, this is a constant. The derivative of this is going to be 2y. The derivative of this is going to be 4z, and the derivative of this is going to be 1. So you see the partial of w with respect to z is going to be 2y plus 4z plus 1. Now, we often, instead of using this curly notation, we have other notations as well. That's what happens in math. So if we write f sub x of xy, or fx, that's the partial of f with respect to x. And similarly, this is the partial with respect to y, and this would be the partial of z with respect to x, would be zx, and then z sub y. And so you see that's additional notation, and often that is used, and you should familiarize yourself with that notation. Okay, suppose we have another example. F of xy is equal to this. You want to find the partial with respect to x and the partial with respect to y. Well, okay, so here you're just going to be taking the derivative. You're assuming that y is a constant, and so you're going to get 6xy plus y squared. Make sure you can duplicate these calculations. Here, since we're taking the partial with respect to y, the x is a constant, so this is going to be 3x squared. And this, we're taking the derivative with respect to y, so that is 2xy. Make sure you can follow those. And sometimes I will ask you, in fact, more often than not, I will ask you to evaluate these. That means plugs in numbers. So we're saying, what is f sub x at 2 comma minus 3? Well, we substitute 2 comma minus 3 in, and for x and y respectively, and do the calculation, and we get negative 27. Let's do another example. This has exponentials and logarithms in it. So f of xy is e to the xy plus y ln of x. We want to find the partial with respect to x and the partial with respect to y. Well, here we have to use the chain rule. So the derivative of this is going to be e to the xy times the derivative of this, and again it's with respect to x, so it's going to be y. So this first term is going to be y times e to the xy plus y is a constant, so I'm really just taking the derivative of ln x, so that is 1 over x. And so that is what this is, and I can simplify that a bit. And if I multiply these together and that together, I can write it more compactly like this. Similarly, we're going to get this. Now here, the x is a constant, so the x comes down from the chain rule. And here, the ln x is a constant times y, so that is just ln x. Make sure you understand these as you go through. One model of production that's frequently applied in business and in economics is called the Cobb-Gliss production function. And it's like this. The production that is possible at values x and y is equal to a, and this is x to the a. This was a capital A, that's a lowercase a, and this is y to the 1 minus a, and a is a number between 0 and 1, and capital A is some number greater than 0. Where P is the number of units produced, with X units of labor and Y units of capital. Capital and labor are considered different things. Capital is the cost of machinery, buildings, roofs, and other supplies. And labor typically is people that you have, how much you're paying for them, how much you're paying for the benefits. So the partial derivatives then, the partial of p with respect to x and the partial of p with respect to y, are called respectively, and this shouldn't surprise you from what we've studied before, the marginal productivity of labor and the marginal productivity of capital. Again, an example is useful. So you have this cellular company that has this as their production function for a smartphone. So P is the units, is the number of units produced with X units of labor and Y units of capital. So here we're supposed to find the number of units produced with 125 units of labor and 64 units of capital. You just substitute these in. Now you should make sure that you can substitute those in, because if I ask you a question like this, you want to be able to answer it. And so we're going to have substituting that in just to my original function, which is here. And I have to be able to take these to the 2/3 power. I'm going to get 5,000 units. But now I'm asked about find the marginal productivities. That means the partial with respect to x and the partial with respect to y. So the partial with respect to x is going to be, we're treating y as a constant. So that means I'm treating x as a variable. So I'm going to say the 50 just sits there, and the y to the 1/3 just sits there. But then this is going to be 2/3 x to the minus 1/3. And you see there's 2/3 x to the minus 1/3 times y. So we substitute those numbers in that we had before for x and y, and we can get that, actually they don't ask us to substitute numbers in, but you could. So that's the marginal productivity here. The marginal productivity of capital is the partial of p with respect to y. Could be written this way. I'm doing the y. Now it turns out that y is 1/3, so that's going to be 1/3 y to the minus 2/3, and we get this. Now those would be numbers, and I could ask you to plug in numbers there, and I guess that's what we ask you to do here. So we're using the same values, x is 125 and y is 64, so what do we get when we plug into these? And you see we get 26 and 2/3 and 26 and 1/24. Now let's interpret what that means. So that means the marginal productivity of labor, suppose capital is fixed at 64 units, then a 1 unit change in labor from 125 to 126 will cause production to increase by 26 and 2/3 units. To visualize the productivity of capital, suppose labor is fixed at 125, then a 1 unit change in capital from 64 to 65 will cause a production to increase about 26 and 1/24 units. Again, you see the meanings are similar to what we learned before about the marginal productivity. Now there are diminishing returns, as we talked about there, because when one, either labor or capital is fixed, and the other increases eventually, the production will increase at a decreasing rate. You get less bang for the buck the further you go out in the function. Totally different topic now. Partial derivatives can also be used to approximate small changes in a function. We did this with differentials before, and we're going to do it with differentials again. Recall from section 3.6 that if we talk about dx and dy being differentials, and those are small changes, and y is f of x, and dx is approximately delta x, and dy is approximately delta y, when these changes are small, what we learn is that the change in y is approximately f prime of x times delta x. So here we're doing the same thing, except we're going to be using both partial derivatives. For functions of several variables, the differentials of each function are similarly related. So if z is equal to f of xy, then we have dz, the change in z is approximately, this is the partial of f with respect to x, times dx, the change in x, plus the partial of y with respect to y, dy. And these are the values, and those are the changes. Let's look at an example of that with tolerances. So suppose you have a circular swimming pool that has a radius of 12 feet and a depth of 4 feet. And over here you've got the radius is 12 feet and the depth is 4 feet. So we want to find the volume of it, assuming those are the radius. Well, we have to know what is the volume here. And the volume by a general geometry formula is it's the volume of a cylinder. So it's the area of the base and the top, by the way, times the height. So the area of the base is pi r squared h. So you see the volume as a function of r, and h is pi r squared h. So if we're taking in part A the radius to be 12 and the depth to be 4, we'll substitute that in, do the calculation, and we could treat pi as just a number. The exact answer is 576 pi, or if we take pi in a calculator, that's about this many cubic feet. So that's what the volume of this pool is. But now, in part B, we're saying, let's use differentials to estimate the change in volume, assuming both measurements include the extra 3 inches. Now, we have to be careful about units because 3 inches, these are feet, so that's going to be a quarter foot and a quarter foot. So we're saying dr is a quarter foot and dh is a quarter foot. So to approximate this, we're going to look at the partial of v with respect to r and the partial of v with respect to h, and this is what v is. So you see, here we're treating h to be a constant, so we get 2 pi r h. Here we're treating r to be a constant, and so when we treat, or excuse me, here we're treating r to be a constant, and h is the variable, so when we take the derivative, you just get pi r squared. So then we can substitute in the formula we had on the previous page. Delta v is approximately this partial times dr, and this partial times dh. But if we put r to be 12, h to be 4, delta r and delta h both are 1/4 foot, then we find that this delta v is approximately, and we substitute in, and that ends up to be 60 pi. That's the exact answer, or if you use your calculator, you get this. This is very similar to problems that I've asked before, so make sure you understand that and can follow these calculations. Now, in the same way that before we talked about second derivatives, we can talk about higher order partials. But now we're going to have two kinds of things. We can take the partial with respect to x twice. We can take the partial with respect to x, the partial with respect to y, the partial with y with respect to x, and then we can do the partial twice with respect to y. So you see there are 4 different partials we could take. But these are higher order partials because we take more than one partial derivative. So again, let's consider this function, z equal f of xy equal 3x y squared plus 2xy plus x squared. Then the partial of z with respect to x is this. Now suppose we want to have then the partial of that with respect to y. So we're going to take this, and we're going to take the partial with respect to y, and that will give us this. Now notice that this notation works this way. We get d and d, we're going to call that d squared, and here we got this is the second partial we take, and that is the first partial that we take. So this is what we get when we take that partial derivative with respect to y. And so that notation could be listed this way, or this way. Here you're using z, here you're using f, or it could be this, f of xy. Now in the notation f of xy, it's important to note that the x and y are in the order left to right, which is the differentiating is done. In this notation, the order of x and y is reversed. That can be confusing, but I will tell you why that's not quite as big of a deal as you might think it is as we go forward. So in each case, the differential with respect to x is done first, followed by the derivative with respect to y. So you see, we do have 4 possibilities for second order partial derivatives, and they're listed down here. So here is the second partial with respect to x, all these different notations. Here we can take the partial with respect to x, then the partial with respect to y. Here we can take the partial with respect to y and the partial with respect to x. And here we can take 2 partials, a partial with respect to y and then another partial with respect to y. Now it turns out we're going to be using these second partials later, just like we had a second derivative test before. So you do want to pay attention to this as well as being able to do these calculations. Okay, so here in example 6, we're calculating these. So for z equals f of xy equals this, notice that we have an exponential here. Find the 4 second-order partials. So we take the partial with respect to x twice. This is the partial first with respect to x, then with respect to y. This is a partial first with respect to y, then with respect to x. And this is a partial with respect to y twice. Now you should go through and verify that you follow these calculations. So this is the answer we get for part A, for part B, part C, and part D. Now notice that here, this answer is the same as this answer. So if we compare parts B and C, we see that those second partials are equal. Now this is not always true. In fact, I know quite a bit of math, and I'll tell you that's only true whenever these second-order partial are continuous functions, then they're the same. But that will be true for almost all the functions we consider in this textbook. But it's not true for all functions, and there is an example in exercise 67 if you want to look at one where it is not. And in a later section, very soon, we'll see how these higher order partials are used in applications to find extrema for functions of 2 variables, a very important application that I might ask you about sometime. So keep that in mind. For now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless.